Hello class, welcome to today's lesson. For today's lesson, you're going to want your notebook or some scrap paper for the warm-up. And then for the lesson itself, I did attach a handout that you might want to print to today's announcement in Google Classroom. If you can't print the handout or don't want to, you can just do everything in your notebook. So for the warm-up today, we're going to do two things. The first one is we're going to sketch the graph of y equals x cubed because you need to know what that looks like for today's lesson. So this equation should sound familiar. We talked about it a couple chapters back when we were talking about end behavior. And if you remember, I would stand in the front of the room, and if I raised both my hands up, we thought of x squared. If I put both my hands down, we thought of negative x squared. And then if I put one hand up and one hand down like this, that was what x cubed looked like. And negative x cubed would be flipping that. So what x cubed looks like, if we did a quick sketch, it would look like this. It goes through the origin, it curves up like that, goes up to the right, and it falls to the left like that. So to be a little more precise, we can make a quick table. And if we plug in 0, 0 cubed is 0. That's why it goes right through the origin. If we plug in 1, 1 cubed is 1. If we plug in 2, 2 times 2 times 2 is 8. And I went ahead and put 8 tick marks on my y-axis when I set that up. And then we can plug in some negatives as well. If we plug in negative 1, we get negative 1. And if I plug in negative 2, I'll get negative 8. And we could keep this graph going. We could plot more points, but that's all it's going to fit pretty reasonably, because if we were to plug in 3, we'd be up to 27 already, and that's too high up for the sketch that I started. So that's what y equals x cubed looks like, and we'll be referencing that later today. For the next part of the warm-up, I want to review this. Do you remember what that symbol is called? Okay. And for the composition, it's called a composition. And what this means is we want to find f of g of x. So we want to put the function g of x inside the function f of x. So the way we do that is we replace g of x with whatever it's equal to. So g of x is x squared plus 4. So I've replaced g of x with the expression it's equal to. And then what we want to do next is we want to go into the function f and replace x everywhere we see it with this expression. So when I taught this, sometimes we lined it up right above. Sometimes we grabbed a different color for that. So instead of x, we're going to put x squared plus 4. So I'm going to keep the square root. I'm going to keep the 2. Instead of x, I'm going to put x squared plus 4. That requires parentheses because I replaced the x with 2 terms. And then I keep the plus, and then I keep the 3 all underneath the radical. So that's the composition f of g of x, and we're just going to simplify it a little bit by distributing the 2. And you can't do anything to simplify it further, so that's your composition f of g of x for this example. Okay, next, to begin today's lesson, we are going to be talking about section 5.6 today. This is the last section in chapter 5, and it's going to be about inverse functions. So informally, inverse functions undo each other. So what that means is when you're looking at an equation, if you see a plus 2, you're probably going to see a minus 2 in the inverse. If you see times 5, you're probably going to see divided by 5 in the inverse. You're going to see, a lot of times we call them opposite operations, but they're really inverse operations. And I'm not going to write down those examples right now because that's informal. That's not a foolproof way to know that you have inverses. So I'll mention it. I'll bring it up again later today. I'll bring it up again in the next lesson. But I'm not going to write down notes on that informal way of thinking. So for inverses, the first thing we want to do is learn how to find an equation of an inverse. So to find an equation of an inverse, we replace f of x with y, switch x and y, solve for y, and change back to function notation if possible. So for this example that I made up, I have a cube root function, and we are going to replace f of x with y. And then we're going to switch x and y. So we actually swap where they are. So x goes here, y goes here, which is a little different than the way it was done in the Khan Academy video yesterday. But I think you'll find that you like this way a little better than what he did. So I like to switch x and y and then solve for y. So to get y alone, we want to start to move things away. What's the first thing we can move away? Can we move the cube root, the -4, or the +2? The +2 is what we can move first. So we're going to subtract that over. And next, you can move the cube root. You can get rid of the cube root, but you can't get rid of the -4 yet. You can't go adding 4 to both sides at this step because that -4 is trapped inside that radical. So you do have to do things in a certain order. So what we want to do next is we want to get rid of that cube root. So to get rid of cube root, we can cube both sides. I wrote the wrong number. Sorry about that. When I copied that down, I wrote 3 by accident. Okay, so cube and cube root are called inverses. They're going to cancel each other out. And then this x minus 2 to the third, we could work that out. But I'm going to say let's just leave it as x minus 2 to the third. One reason is because this would be an awful lot of work to do. And the second reason is will become clear as we continue our examples. So continuing on our way, our goal was to solve for y. So our final step is to add 4 to both sides. You can't add the 4 to the 2 because the 2 is trapped inside with the cubed. So the best we can do is just write a +4 at the end. And now that we have y by itself, we can change to function notation by putting f inverse. So we don't read that f to the -1. The way we read that is f inverse. And that is what the inverse of the original function is. And if you look, we can talk about that informal way of thinking about these inverses. Do you see how this one has a +2 and this has a -2? You'll see that very often when you have inverses. See here, there's a -4 and here there's a +4. You think of those as opposites usually, but in math, we're going to call them inverses. And then you have cube root, and the inverse of that is cube. So now that we found our inverse, what I'd like us to do is I would like us to graph the original function and the inverse on the same plane. So for the function f of x, that's cube root x minus 4 plus 2. That is your cube root graph. Move 4 to the right and up 2. Now, I know that you know how to graph that, but just to save us some time, I'm going to tell us the points to use. So we're going to plot 4, 2. And then we're going to plot 5, 3. 3, 1 is also on the graph, so go to 3, 1. And -4, 0 is also on the graph. So if you plot -4, 0, 3, 1, 4, 2, and 5, 3, that should be enough points to plot. When you go to do this graph, you should curve like that going up to the right, and it should curve like this coming down to the left. And let's go ahead and label that graph as f because we're going to put the other graph on the same plane. F inverse of x was x minus 2. That quantity is cubed and then a +4. So what I did is I went ahead and made a table and found some points on that graph. And to save us time, I'm just going to tell you what to plot. So for f inverse, you can plot 2, 4. I'm going to grab a different color. You can plot 2, 4, 3, 5. Plot the point 1, 3. And then 0, -4. And what you should do is from this point here at 2, 4, so look at 2, 4, curve up like this, going up to the right, pretty steep, and then come down to the left like this. Make sure you pass through 0, -4. And if you picture me at the front of the room right now, are you seeing that that's your cube root graph from our cubic graph from the warm-up? So this is your x cubed graph, but it's been moved. And notice if we think of our transformations, it's been moved 2 to the right, and the +4 has also moved the graph. How did the plus 4 move the graph? So this is our basic cubic function, move 2 to the right and up 4. Now, if you take a look at these two graphs compared to each other, just like you saw in the Khan Academy video yesterday, they are reflections of each other over the line y equals x. So I'm going to go ahead and put in the line y equals x, but I'm going to graph that as a dashed line. So that dashed line should go through 1, 1, 2, 2, 3, 3, 4, 4, all the way out to 10, 10, all the way down to negative 10, 10. It should split right through the middle of quadrant 1 and right through the middle of quadrant 3. And the reason we make that graph dashed is because it's not technically part of the graph we're looking at. It's just to allow us to see that we have reflections. This point flipped over this line goes here. This point flipped over that line y equals x goes here. If we flip from the first graph to the second graph, this point flips to here. In geometry, you called it a pre-image and an image. So if this is the original and you flip it, that's your pre-image and image. You don't need to know those words for this year. So from our example, we can see that if we have inverses, they're going to be reflections of each other over the line y equals x. That's going to happen every single time you have inverse functions, not just for this pair. But anytime you have inverse functions, they will be reflections of each other over the line y equals x. Okay, so that's a property of inverse functions we should be aware of. The next property of inverse functions for us to be aware of is what happens with the ordered pairs. So remember those points that I named for you before so that you could get your graph? Well, now go ahead and take a moment and show for our example that the points we plotted on f of x, we plotted 4, 2, 5, 3, 3, 1, and negative 4, 0. Those are just some of the points on f of x. Those are the ones we used to make the graph. And on the inverse, we plotted 2, 4, 3, 5, 1, 3, and 0, negative 4. And if you look at the relationship here, I think you can see that the x and the y have switched. Inverses are all about switching x and y. All right, if you think back to how we found the equation, we switched x and y. If you look at these ordered pairs, you switch x and y. So instead of 3, 1, you have 1, 3. So a property of inverses in general, because this is true for the pair of functions we have, but we're going to be looking at other examples of inverses over the next couple of days. So for any pair of inverse functions, if you have a point, let's call it AB, on the graph of f, then what point has to be on the graph of f inverse? BA, because you switch x and y. So instead of AB, BA will be on that graph. And we can continue with our properties of inverses by looking at a special pair of points. For inverses, x and y intercepts are going to switch because inverses are all about switching x and y. So if you have a y-intercept on your graph of f, then you're going to have the x-intercept on the graph of the inverse. Because think about this. If 0c is on the graph of f, then c0 has to be on f inverse. And that would be an x-intercept. And if you have c0 as an x-intercept on your original, then if you switch x and y, you're going to get 0c, and that's got to be on the inverse. So what was an x-intercept on f becomes a y-intercept on the inverse. And I want to take you over to Desmos for a moment to show you that. So here's the example we've been working on. And if you look at the some of the points here, you can see that here's a 2, 4, and 4, 2. We can see the x and the y have switched between the graph and its inverse. And if we take a look, we can see the intercepts. So we did plot on the cubic, this is our cubic function. We plotted 0, negative 4. And on our cube root function, we plotted negative 4, 0. So this special point right here is an x-intercept. And because we switched the x and y to get the inverse, it becomes a y-intercept on the inverse graph. That also happens with the x-intercepts. The x-intercepts are not going to be such nice numbers. They're going to be kind of crazy decimals, but we can still see that relationship here. So here's the decimal approximation for the y-intercept of the red graph. And when we reverse the x and y, when we switch x and y, we end up with an x-intercept on the green graph. So again, the x and y intercepts have switched. We have one more property of inverses to discuss today, and that's what happens algebraically with the equations. So another property of inverses is that when you do the composition, which is why we warmed up with compositions, if you put F inverse inside of F or put F inside of F inverse, what's going to happen is everything's going to cancel out and you're just going to get X at the end. And that's going to happen with every single pair of inverses. So let's take a look at our example and see what happens. So F of X from our example was cube root of X minus 4 with the plus 2 outside. And F inverse for our example was X minus 2 quantity cubed with the plus 4 on the outside. And my claim here is that because these are inverses, if I were to compose and do F of F inverse of X, when we're finished, everything should cancel out and we should be left with just X. So let's do that work now. So if I want to find F of F inverse, I'm going to replace F inverse with X minus 2 cubed plus 4, because that's what F inverse is equal to. So I've replaced F inverse with the expression it's equal to. So now I want to find F of this entire expression. So this is where in the past it helped some of you to grab a different color and write the original function right above. So F of X itself is cube root of X minus 4 with the plus 2 outside. And what we want to find right now is F of this mess. So instead of X, we're going to put this whole expression. So I'm going to keep the cube root. I'm going to replace X with this entire thing. I don't actually need parentheses around it, but I'm going to go ahead and throw some brackets in just so I know that that's what I replaced X with. Then I have to keep that minus 4 that's underneath the radical. And then I have to keep that plus that's outside and keep that 2 that's outside. So take a look before you continue. We've replaced X with this entire expression. Our next job is to simplify. And when you do this, I'm going to ask you to show all your steps, because what we're going to have to make sure of is that you are doing your algebra in the correct order. You want to make sure you're following order of operations. Because if you take a look at what we're doing, I think you'll see that the cube and cube root will cancel, but you can't cancel them right now. You can't cross those out now. The 2 here and the plus 2 outside are going to cancel, but you can't cross them out now. You can't cross out that minus 2 and that plus 2 because the minus 2 is trapped inside parentheses with a cube with all this other stuff. So even though everything is going to cross out, you have to do it in a certain order. So the only thing you're allowed to cross out right now is the minus 4 plus 4. So go ahead and cancel those out. And then think about what we can do next. We can cross out cube and cube root. Those are called inverses and they undo each other. And now all I have left is X minus 2 plus 2. Now the 2's can cancel out and I'm left with X as we predicted. Now we said the composition both ways should come out to X. So now let's try the composition the other way where we put F inside F inverse. So what we're going to be finding is F inverse of the cube root of X minus 4 plus 2. And remember, compositions are not commutative. So if you reverse the order of the composition, the work is going to be different. So we want to find F of that. F inverse, I'm sorry. We want to find F inverse of that. So if it helps you, grab a different color. And write down what F inverse is right above. Because what we're going to do is we're going to replace X. We're going to replace X with this entire expression. So I'm going to keep the parentheses. In place of X, I'm going to put this. Then I'm going to keep the minus 2. So I'm going to put parentheses around that, even though they're not quite necessary, just to show what we replaced X with. Then I keep the minus 2. Then I close the parentheses. Then I put a cubed. Then I put a plus. Then I put a 4. So these should look exactly the same. except instead of X, I put all of that. Instead of X, I put all of that, and then I kept everything else. So I'm going to rewrite that because it's a little squishy in there. And as I mentioned, I don't actually need these parentheses, those inner ones. Okay. So like I said last time, when we do this type of work, I am going to ask to see all the steps because I want to make sure that you're canceling things in the correct order. I want to make sure you're not breaking PEMDAS or order of operations. What are we allowed to do first in this problem? Cancel the cube root and cubed, cancel the 4s or the 2s? The 2s. Last time, it was the 4s we canceled first. This work is different because we're doing the other composition. Now we're putting F inside of F inverse, so the work will be different. Next, we can cancel cube and cube root. We cannot cancel -4 and +4 right now because that -4 is trapped inside all this other stuff. But cube and cube root, we can cancel those out. And then finally, if we cancel the 4s, we end up with X as our final results. So as promised, as predicted, when you have inverse functions, if you do the compositions, everything's going to cancel out. You're just going to be left with X. So that's today's lesson. And it was just one pair of examples of inverses. So I don't expect you to be 100% comfortable with this information yet. But hopefully you're around 75% comfortable with the information. And next time our class is scheduled to meet, we will give you some practice on this material so that you can get more comfortable with it and get that practice that you need. Thanks, guys. Have a nice day.